There is something wrong with the sand, not the color, not the temperature, not even the silence that spreads across 9 million square kilometers of Africa's northern face like a held breath. What is wrong with the sand is the size of it, the shape of it, the impossible, relentless industrial consistency of it. When geologists first began studying the grain structure of Saharan sand in the late 19th century, they expected what you would expect from any natural desert system. Variation, a wide spread of particle sizes shaped by different rock types, different erosion processes, different distances, travelled by different winds over different centuries. What they found instead quietly unsettled the field for 150 years. The grains were uniform, not loosely uniform, not within a reasonable natural range. They were uniform in the way that a manufactured product is uniform, sorted, sized, processed. The dominant grain diameter across the central Sahara measures between 0.2 and 0.3 millimeters. This places almost the entire desert within what industrial engineers classify as medium-grade silica sand. Not coarse, not fine, not variable, medium, consistent, repeatable. If you filled a shipping container with Saharan sand and sent it to a construction materials testing laboratory, the laboratory would classify it as a commercially viable, grade-consistent aggregate. It would pass industrial specification without modification. This is not how natural sand is supposed to behave. Natural weathering processes are messy. Rivers carry material of wildly different sizes. Wind erodes different minerals at different rates. Frost shattering produces angular fragments. Coastal wave action rounds pebbles but also deposits silt. The mountains and plateaus that supposedly fed the Sahara with their eroded material over millions of years are composed of different rock types in different locations, which should have produced a desert floor with radically different grain populations in different zones. You should be able to walk from one region to another and feel the difference underfoot. You should see the record of geological complexity written in the sand itself. Instead, the Sahara is consistent, monotonously, mathematically consistent. And the question that no one in mainstream geology has ever satisfactorily answered is, what process, operating at a scale of 9 million square kilometers, sorted and sized and deposited sand to that level of industrial precision? The official answer has always been wind, aeolian processes. The idea that wind is a natural sorting mechanism, that lighter particles blow away and heavier particles settle, that given enough time the Sahara would naturally arrive at a relatively consistent grain profile. This explanation is taught in universities. It appears in textbooks. It is repeated so often that it has taken on the character of certainty. But when you actually sit with the numbers, the explanation begins to fall apart. Wind sorting is real. It does produce some degree of grain size differentiation, but it operates over distances, not across an entire continental mass simultaneously. Wind-sorted deserts show consistent gradients, finer material downwind, coarser material upwind. The grain size changes as you travel in the direction of the prevailing wind, because lighter particles have traveled farther. The Sahara does not behave this way. Its grain profile does not follow a wind gradient. It sits in a narrow size band across regions that are separated by thousands of kilometers and fed by entirely different source rock systems. No single wind event, no series of wind events, no amount of time spent running aeolian physics models produces that result from natural starting conditions. There is a second answer that mainstream geology reaches for when the wind explanation strains credibility. Ancient rivers. The idea that during previous wet periods the Sahara was crisscrossed with river networks that sorted the sediment before the climate shifted and the rivers dried up. This is at least partially supported by evidence. Radar imaging from space has revealed the ghost lines of enormous ancient river channels buried beneath the sand. These paleochannels are real. The rivers existed. The Sahara was, at various points in deep history, a place of running water. But rivers also sort material by size and type. And river-sorted sediment has a signature. It has layers. It has variation. It has a record of flood events and dry periods written into its stratigraphy. Deep drilling into the Saharan sand body does not reliably produce that record. What it often produces is a deposit that looks, to an honest eye, less like the product of a river system and more like a dumped fill. This is the observation that has circulated quietly outside mainstream academia for decades now. Researchers examining core samples from deep Saharan drilling operations have noted that the sand lacks the expected stratigraphic complexity. It sits there in bulk, consistent, deep. Without the organic inclusions, the layered record, the textural variation that any natural depositional system leaves as its fingerprint. And beneath the sand, in some locations, there are things that should not be there. Mining operations across the Saharan and sub-Saharan fringe have encountered at various depths surfaces that behave like processed floors, vitrified layers, material that has been exposed to temperatures that no natural geological process operating at that location and time period can explain. Fulgurites, which are the glass tubes formed when lightning strikes sand, do exist and are documented, but the glassy infused layers found in certain Saharan subsurface profiles are too laterally extensive to be explained by lightning. They cover areas measured in hundreds of square meters, in some cases kilometers. The most famous example sits above ground and has been studied for almost a century. Libyan desert glass is scattered across an approximately 6,000 square kilometer area in the southwestern corner of Egypt, near the Libyan border. It is a pale, yellow-green silica glass of extraordinary purity, formed at temperatures exceeding 1500 degrees Celsius, found in fragments and nodules on the surface and in shallow subsurface deposits. It is old. Estimates place its age at approximately 26 million years by mainstream dating, though that figure carries significant methodological assumptions that have been contested. What is less contested is that the glass exists, that it required extreme heat to form, and that the official explanation has shifted multiple times. The current preferred mechanism is a meteorite airburst or surface impact, based on the presence of microscopic diamonds and certain mineral phases that indicate shock pressure. This explanation is plausible. It may even be correct. But there are other glass deposits in the Sahara that do not carry the same impact markers, that are not associated with any identified crater or impact zone, that are simply there, fused, processed, sitting in a landscape that is already made of inexplicably sorted, inexplicably uniform, inexplicably processed-looking material. At some point, the word inexplicably begins to function differently. Every time the word appears, it is a placeholder. It holds the space where an explanation should be, but is not. And when a landscape generates inexplicably, enough of those placeholders, a different hypothesis begins to demand attention, not because it is comfortable, not because it is provable in the way that laboratory experiments are provable, but because it fits the observable data in a way that the official explanations do not. The hypothesis is this: the Sahara is not a natural desert. It is a waste deposit. It is the industrial tailings of a civilization that operated at a scale and with a level of material processing capability that our current historical framework cannot accommodate. To understand what mining tailings look like, you need to spend some time around active mining operations. When rock is crushed to extract ore, the process produces enormous quantities of waste material. This material, the gangue, the spent rock, the processed aggregate, is moved to tailings facilities. Modern tailings dams are some of the largest engineered structures on Earth. The waste rock from a single large open pit mine can fill a valley. The grain size of processed mining waste is not random. It reflects the crushing and milling parameters of the operation. It is sorted, it is sized, it is, in its own way, consistent. If you took a tailings deposit from a large-scale historical mining or material processing operation and spread it across a continent-scale area, then subjected it to 30 or 40 centuries of wind and weathering, you would expect to find a landscape of relatively uniform grain-size material, depleted in organic content, showing evidence of thermal processing in isolated zones, and sitting above a substrate that carries the ghost of engineered surfaces. You would find, in other words, something that looks very much like the Sahara. The question of what was being mined has generated significant discussion in alternative research circles for the last 2 decades. The Saharan and North African substrate is rich in mineral wealth: gold, iron ore, uranium in significant concentrations, manganese, phosphate. The African continent holds some of the largest known reserves of these materials on Earth, and the northern third of the continent, currently buried under sand, sits above geology that is continuous with the mineralized belts of the sub-Saharan interior. If an advanced civilization was extracting mineral wealth from North Africa at industrial scale, It would have for both the resource base and the motivation to do so. There is also the question of what happens to rock when you process it at scale. The dominant mineral in Saharan sand is quartz, silicon dioxide. Quartz is extremely durable and chemically stable, which is why it survives weathering. But quartz is also what you are left with after you have removed the economically useful components of granite and similar rock types. When you crush granite, process it for its mineral content, and discard the gangway, the residual material is heavily enriched in quartz because the ore minerals, the metals, the economically valuable components, have been extracted. The Sahara is overwhelmingly quartz. The explanation offered is that quartz is simply what survives long-term weathering because it is resistant. This is true, but it is also exactly what you would predict if the material had been processed to remove its valuable components before being discarded. Two explanations that both fit the data. One of them does not require a civilization. One of them does. The one that does not require a civilization is the one that appears in the textbooks. The Green Sahara complicates this picture in ways that are rarely discussed in mainstream presentations of climate history. Between approximately 11,000 and 5,000 years ago, the Sahara was wet. This is not a fringe claim. It is established paleoclimatology. Cave paintings in what is now the empty Algerian interior show cattle, hippos, crocodiles, humans swimming. Pollen records from lake beds show forest cover. Bones of fish and water buffalo have been found hundreds of kilometers from the nearest contemporary water source. The Sahara was habitable. It supported dense populations of large animals and, by implication, dense human populations. Then it dried out, rapidly by geological standards. The African humid period ended and the desert returned to something close to its current state within a few centuries, possibly even faster. The mechanism was a shift in the orbital parameters of Earth, specifically the precession cycle that affects the intensity of the West African monsoon. This is the official explanation, and it has merit. Orbital forcing is real and documented, but orbital forcing alone, as several climate modelers have quietly noted, does not fully account for the speed of the transition in some regions, and it does not account for the failure of the vegetation to recover during subsequent orbital cycles that should have reproduced the monsoon conditions. The Sahara today behaves differently from the Sahara during the humid period in ways that suggest the surface itself has changed, not just the climate, but the land. Something about the ground of the Sahara resists revegetation in a way that models of climate-driven desertification struggle to reproduce. A surface made of processed tailings, depleted of organic material, compacted by enormous historical loads, and chemically altered by thermal events, would resist revegetation. It would behave differently from weathered natural bedrock. It would drain differently. It would reflect heat differently. It would be, in the language of agriculture, a dead substrate. The Sahara is extraordinarily difficult to revegetate. Projects to restore vegetation cover have faced challenges that go beyond the simple lack of rainfall. The soil, or rather the material that should function as soil, does not respond in the ways that degraded natural soils respond to remediation. It behaves like something that has had its biological and chemical complexity removed at source. This brings us to the other deserts. The Arabian Desert covers approximately 2.5 million square kilometers. Its sand shows a similar uniformity of grain size to the Saharan material. Like the Sahara, it sits above a substrate that is extraordinarily rich in mineral resources. The Arabian Peninsula contains some of the world's largest hydrocarbon deposits, which represent ancient organic matter, but also significant metal ore deposits in the ancient shield rocks of its western margin. Like the Sahara, the Arabian Desert shows evidence of ancient habitation during periods when the climate was wetter, and like the Sahara, it has failed to naturally revegetate during subsequent humid periods. The Gobi Desert, sitting across Mongolia and northern China, is the world's 5th largest desert. Its grain profile shows the same suspicious consistency. It sits above one of the most mineralized geological zones on Earth, containing enormous deposits of copper, gold, coal, and rare earth elements. The Gobi shows ancient habitation layers that predate any known historical civilization in the region, and it contains the same kind of anomalous hard layers and vitrified zones documented in the Sahara. The pattern is not confined to one desert. It is not a local anomaly. It is a global signature. and global signatures require global explanations. The hypothesis that has emerged from researchers working at the intersection of alternative archaeology, materials science, and what has been loosely called the Tartarian framework, holds that the major desert zones of the Old World are not independently formed natural features. They are the waste deposits of a single civilization, or a network of related civilizations that operated across the connected landmass of Africa, the Middle East, and Central Asia during a period that mainstream history places outside the range of complex human activity. The dating problem is significant and cannot be dismissed. If the Sahara tailings were deposited before or during the Green Sahara period, or if the Green Sahara itself represents the period of active operations before the abandonment that created the desert conditions, then the civilization responsible would have been operating between 5,000 and 12,000 years ago at minimum. This places it contemporaneous with the accepted origins of agriculture and early urbanization. But the scale of the proposed operations, the volume of material moved, the thermal processing implied by the glass zones vastly exceeds anything attributed to any known civilization of that period. The alternative, which some researchers in this space have proposed, is that the dating is wrong. Not slightly wrong, fundamentally wrong. That the material in question is not 12,000 years old, but significantly older, and that the dating methods applied to it are producing spurious results because they are measuring the wrong things or operating on assumptions that do not hold for processed industrial material. This is where the discussion moves into territory that requires serious intellectual honesty about what we know and what we assume. Radiometric dating of geological material is not infallible. It depends on assumptions about initial conditions that cannot always be verified. For material that has been thermally processed and subjected to high temperatures that can reset or contaminate radiometric clocks, the dates produced can be significantly in error. Libyan desert glass has been dated by multiple methods with results spanning a range of millions of years, depending on the method and the specific sample. The consensus figure is approximately 26 million years. But a consensus among methods that each carry their own assumptions is not the same as a verified absolute date. If the major desert deposits of the Old World are 500,000 years old or 1,000,000 years old, the civilization responsible would be operating at a time period that falls entirely outside the framework of human history as currently constructed. This is not a comfortable conclusion. It requires revising the story of human cognitive and technological development in ways that have cascading implications for almost everything else in the historical and archaeological record. And yet, the sand does not care about discomfort. The sand sits there, 9 million square kilometers of it, grain by grain identical, quartz by quartz depleted, layer by layer stripped of the organic complexity that natural geological processes leave behind. It sits in the same narrow size band from Morocco to Egypt. It resists the rain, it resists the seed, it reflects the heat back into the atmosphere and maintains the conditions of its own desolation. The Egyptians built at the edge of it, the Romans crossed it, the Arab traders found routes through it. Every civilization that encountered the Sahara treated it as a given, as a background condition of the world, as something that had always been there. None of them seemed to have wondered what was under it, or what it had been before, or who or what had made it into the thing it was. We are better equipped than they were to ask the question. We have satellite imaging that can see through sand to the structures below. We have geochemical analysis tools that can characterize the processing history of individual mineral grains. We have subsurface radar systems that have already revealed the ghost rivers and the buried hard layers that no official explanation has satisfactorily accounted for. What we lack is the institutional will to apply those tools to the question being asked here. Not to the question of ancient river channels or paleoclimate reconstruction, but to the specific question: was this material processed? Does it carry a chemical and textural signature consistent with industrial scale crushing and separation? Are the vitrified layers the byproduct of a thermal processing technology rather than a natural or cosmic event? These questions are technically answerable. They are not metaphysical. They are materials science questions that could be investigated with existing laboratory technology applied to existing core samples. The investigation has not been systematically conducted, at least not in any published literature that is accessible to open inquiry. The absence of the investigation is itself a data point. In science, the questions that are not asked are as informative as the questions that are. And the question of whether the world's major deserts are natural features or anthropogenic waste deposits has not been seriously asked within institutional science in the entire history of the discipline. Some researchers have pointed to the ancient mythological and religious traditions of North Africa and the Middle East as an additional line of evidence. The traditions are diverse and complex, but certain themes recur. The theme of a previous world, a previous people, a previous age of building and making that ended in catastrophe. The theme of fire from the sky, the theme of land that was made uninhabitable by the actions of a powerful civilization or force acting against it. These themes appear in the oldest layers of Sumerian, Egyptian, and Berber tradition. They appear in forms that predate the written record in rock art and ritual practice. Mythology is not history. It is not evidence in the scientific sense. But it is a record of collective memory, and collective memory does not generate specific, recurring, geographically consistent themes without some referent in experience. When the oldest traditions of the people who live at the edges of the world's largest desert consistently remember a time when that desert did not exist, and when they remember something that ended it, the question of what that something was is worth asking. There is also the matter of what is not in the sand that should be if it were natural. Soil biology depends on the presence of organic matter, microbial communities, and the slow accumulation of biological debris over time. Even very old desert soils that have never been vegetated carry some trace of biological activity, because biological activity is pervasive and accumulates even at low rates over geological timescales. The Saharan sand body contains extraordinarily little organic material. Its microbial community, while it exists, is far sparser and less diverse than would be predicted by models of long-term natural desert formation. The material behaves as though it was deposited recently, or as though it was processed in a way that removed or destroyed the biological component before deposition. This is consistent with tailings. Processing operations that use chemical or thermal methods to extract minerals from rock produce waste material that is chemically and biologically depleted. It is not consistent with a desert that has been forming naturally for millions of years. A million-year-old desert should be, in its own way, biologically rich. It should carry the accumulated biological record of a million years of life, attempting to colonize its surface. The Sahara does not. The iron content of Saharan dust has been a subject of significant scientific attention because of its role in fertilizing the Atlantic Ocean and the Amazon basin. Saharan dust, transported by trade winds across the Atlantic, deposits iron and phosphorus that drives biological productivity in nutrient-poor ocean and forest systems thousands of kilometers away. This is a well-documented phenomenon. What is less commonly discussed is that the iron in the dust exists in forms more consistent with material that has been through a high-temperature process than with naturally weathered rock. The Amazon depends on Saharan dust for its fertility. The largest tropical rainforest on Earth, sitting on notoriously nutrient-poor soil, survives in part because of material blown across an ocean from a desert on another continent. If the Sahara is a waste deposit from a processing operation, the fertility of that gangu, its capacity to support life at a distance while unable to support life at source, becomes a coherent property of processed material. The extracted components are gone. What remains feeds the world from a distance, as industrial waste sometimes does, leaching into the broader system as a slow and accidental gift. The megalithic sites of North Africa and the Saharan fringe are less famous than their counterparts in Europe and the Middle East, but they are no less significant. The Nabta Playa site in southern Egypt, dated to approximately 7,000 years before present, contains megalithic stone circles and alignments that predate Stonehenge by several thousand years. Its builders are categorized as pastoral nomads by mainstream archaeology. Pastoral nomads who, in the middle of a habitable but not resource-rich landscape, arranged multi-ton stones with precision sufficient to mark the summer solstice and align with stellar positions. The Atlas Mountains of Morocco contain rock art sites that depict animals now extinct from the region, alongside geometric patterns and figures that do not correspond to any identified natural or biological subject. These patterns recur across thousands of kilometers of rock art sites from Morocco to Sudan. They are consistent. They may be a writing system. They may be technical notation of some kind. They have not been decoded, and the effort to decode them has been like the effort to ask whether the desert is natural, notably absent from the priorities of funded institutional research. What this accumulation of evidence suggests, taken together, is a picture that is coherent if unsettling. A civilization or network of civilizations operating across North Africa and connected regions in a period before the conventional historical record. A civilization with the technical capacity to process rock at continental scale, to produce glass at temperatures that require either very sophisticated furnace technology or a directed energy source of some kind, to construct megalithic astronomical instruments across thousands of kilometers, and to leave behind a geometric symbolic system that persisted into historical periods as unread marks on the walls of the landscape they had made. That civilization is gone. Its buildings, if it had buildings in the conventional sense, are not visible. If they existed in the central Sahara, they are under 9 million square kilometers of the material the civilization produced. Some researchers have suggested that the structures detected by ground-penetrating radar surveys beneath the sand, the anomalous hard layers, the geometric subsurface features that appear at various depths across the Saharan interior, are the remains of those buildings. This is not provable with current data, but it is not ruled out by current data either. The reset hypothesis, which is central to the broader Tartarian framework, holds that at some point in the relatively recent geological past, a deliberate or catastrophic event ended the previous civilization and replaced the record of its existence with conditions that made investigation extremely difficult. A continental-scale tailings deposit over the material evidence of a civilization would be extraordinarily effective at preventing that investigation. You cannot dig through 9 million square kilometers of sand with current archaeological methodology. You can sample it, you can image it, you can extract cores and analyze them, but you cannot excavate it. The desert is, among other things, a vault, and the question of whether it is a vault that was made intentionally or a vault that was made as a byproduct of the industrial process that ended the previous age is one that deserves serious attention. The sand is sized like industrial crush. This is the beginning of the investigation, not the end of it. The uniformity of the grain is a measurable, verifiable, reproducible observation. It does not require belief. It requires a micrometer and a sample. It requires the intellectual honesty to look at the measurement and ask what process produced it, without deciding in advance which processes are admissible. When you take that measurement seriously, when you follow the question where it leads without the institutional filter that decides some conclusions are acceptable and others are not, you arrive at a landscape that is very different from the one in the textbooks. You arrive at a North Africa that was not always a desert. That was made into a desert. That was made into a desert by a process that also produced glass and removed the organic content from the soil and left behind the ghost lines of buried structures under 100 meters of sorted, graded, processed silica. You arrive at a world that is older and stranger and more capable than the one we were taught. A world where the largest desert on Earth is a monument in its own way to something that came before us, something that moved rock the way we move data, something that processed the Earth's crust at a scale we would, if we encountered it today, call civilization without any hesitation or qualification. We do not call it that now. We call it sand. We call it a natural feature. We call it millions of years of wind erosion, and we look at the number and nod and move on. But the sand is sized like industrial crush. The glass is fused at smelter temperatures. The substrate is depleted like worked-out ore. The structures are buried under the tailings. And the oldest people at the edges of it remember, in the oldest layers of their oldest stories, that it was not always like this, that someone made it this way, that something ended, and that the desert is what the ending looks like from the outside. The question is not whether this happened. The question is when we will allow ourselves to look at the evidence and say what it shows. The sand is already telling us. We just have to be willing to listen to what uniform grain size means in a world that does not produce uniform grain size by accident. We have to be willing to ask who sized the grains, and what they were making, and what happened to them when they were done.